Hi there, welcome to lecture 23 of Machine Learning from Data. And today we're going to discuss this all-powerful method called the support vector machine, which is related to the concept of maximizing the margin. Now, let me just remind you that over the past few lectures, we sort of discussed the neural network, or what's called the deep network today. Okay? So, quick review. Now, we started, our models with the linear model and nonlinear transform. So here we have this phi of x is this fixed nonlinear transform. Then, we discussed similarity methods and we introduced the k-RBF network, which ultimately reduces to a linear model where the feature transform are these similarity features. Okay, similarity to what? Similarity to a set of centers, okay, the mu j, and these centers are determined in an unsupervised way. So you, in a mild way, look at the data. Okay. And one way to get those features, the centers, is using k-means, and then we can compute similarity features. Okay. And then the neural network is very powerful. Okay, and if you just focus on the single hidden layer neural network, which basically can implement, as anything you want to implement. Okay, so it corresponds to very finely tuned features. So each hidden node in the hidden layer computes a finely tuned perceptron. Okay, so the neural network generalizes the linear model by, the perceptron by cascading layers of perceptrons. And that's where it gets its power from. And then with that power, we know that you need to regularize. You need to be very careful with that power. Today, we're studying the support vector machine. And again, we're going to go back to the linear model. And rather than cascading linear models to give ourselves more power, we're going to go in the opposite direction. How do we get a more robust linear model? So the support vector machine you can think of in some sense almost as the most robust linear model that you can produce. And in order to motivate this notion of the most robust linear model, I have to remind you that if you're given a set of data, and let's for the moment assume that the data is separable, there are many linear separators that you can pick. So let's take an example. Okay, so here I'm showing you 4 data points. That's just a toy example. I'm showing you 4 data points. Okay, blue, blue, red, red. Okay, and 3 possible separators that you could pick. 3 perceptrons that separate the data. So let's call it left, middle, and right. Okay, now pause the video and decide for yourself which of these perceptrons would you pick. Okay, now we've given ourselves a very nice big advantage. We're humans, okay, and we're looking at the data and we're going to pick visually. Okay, but ultimately, when we say pick, we have to ultimately formulate a quantitative criterion by which to pick. But for the moment, let's just focus on intuition. Which of these classifiers would you pick? Which of these separating perceptrons would you pick? And try to pin down as carefully as you can why. What's your intuition? Okay, so pause the video. 1, 2, 3, 4, 5. Okay, now if you pause the video and said the right one, your intuition matches with mine. Okay, and here's the basic idea. Okay, so you can think that the data is noisy. Whenever you make measurements, so think of you have an x dimension and a y dimension. Whenever you make measurements, there's noise. You don't measure exactly the temperature or the intensity or the symmetry or what have you. Okay, so we make errors when we make measurements, okay? and so we have to accept that the observed data points. Okay, now maybe we don't make so many errors in classifying the data point as a +1 or a -1. So this guy was a bad credit risk. It's relatively obvious if the guy defaults on his credit. So there's no error in the measurement of the y value. So we could imagine that the y values stay the same, but there could be considerable error in the features, the x1 and x2 dimensions. Okay. And so, imagine that I perturbed each data point. So these gray regions in each of these pictures signifies a perturbation of the data. Now, which of these perceptrons will allow me to tolerate the largest possible perturbation in the data and still get the data correct and still get E in 0. Okay. So what we do, we play the following game. We put a little gray circle or sphere in more than 2 dimensions. We put a little gray sphere on each data point. Okay, and let's assume that each data point is going to have, roughly speaking, the same measurement error. So we enlarge, we grow these spheres, and we stop growing the moment we hit the classifier. What that means is that if the data point goes outside that gray region, it's possible for it to get misclassified. Okay? And in the middle, you can see that we can grow these error regions larger and until we hit the perceptron. And on the right, you can grow these error regions quite large until you hit the perceptron on the right. Okay. So what does that mean? So for the separator on the right, what it means is that you could enlarge, you could sustain a significant measurement error in the data and still get E in equal to 0. Okay? And still you can tolerate a lot of error. And now think back to regularization. Think back to regularization. The ability to deal with noise, the ability to sort of be robust to noise and not overfit to noise was the sort of the hallmark of regularization. That's what regularization came in to fix. And what was it fixing? The ability to be misled by noise. Okay? So, if you can tolerate a lot of noise, you are robust to noise. It's very similar to regularization. So this intuition of picking the perceptron, okay, that can sustain the largest amount of error in the data is essentially building in a robustness to noise. It's essentially regularizing. And our intuition matches to sort of what the foundations, what the learning theory says, which is that you should be able to tolerate noise. Noise is always in the data, so regularize. And so when we as humans, intuitively pick the right perceptron, we're implicitly regularizing. Now, another way of looking at this, rather than looking at it from the viewpoint of the data point and putting an error region and growing it. So that's the natural way to sort of view it from the perspective that we're building in robustness to measurement errors. Now I'm going to show you an equivalent way to view that. Okay? An equivalent way to being able to tolerate error in the noise is to imagine that what we're separating with is a hyperplane, is a perceptron hyperplane with some thickness. Think of, my perceptron, and I put a great cushion around it, and now I enlarge the cushion until I hit a data point. Okay. When do I hit the first data point? That corresponds exactly to the size of the region, the size of the error region that would cause that data point to cross this line and my classifier to make an error. Okay. So on the left, the thickness of the hyperplane that's separating this data is actually quite thin. In the middle, it's a medium-sized thickness, and on the right, I can put a cushion and enlarge it quite a bit, okay, and still separate the data. So I'm separating the data with what's called a fat hyperplane. Think of it as a cushion, a margin of error, a fat hyperplane. Okay? And being able to separate the data with a fat hyperplane is equivalent to being able to tolerate noise in the data. It builds in robustness. Okay. So now we can ask the question, well, wow, this is fantastic. So we have now sort of, we can quantify the human intuition of, being robust to noise in the measurement, noise in the measurements, noise in the features through this concept of find me the fattest hyperplane that separates the data. Okay. Now that, in a nutshell, is the support vector machine, or the optimal hyperplane, the maximum margin hyperplane. Okay? And building the math and the theory that allows us to find this hyperplane and justify its use is what we're going to focus on for the next few lectures. Okay? So we're going to sort of address two crucial questions in this realm. Okay? Now, having accepted that the fattest hyperplane, is something that we might want to look at, can we efficiently find the fattest hyperplane? Because remember, we spent a lot of time and effort trying to just, find a hyperplane that separates. And we have this perceptron learning algorithm and the pocket algorithm and so on and so forth. Well, now I'm placing a very complicated constraint. I want the fattest hyperplane. Okay, so I want the fattest hyperplane that separates the data. So for the moment, let's just assume the data is separable. Let's try to solve a simple problem before we go for harder problems. So can we efficiently find the fattest separating hyperplane? Okay. And now intuition suggests that the fattest separating hyperplane is sort of robust to noise, and therefore it's sort of like, in some sense, optimally regularized, maximally regularized, and it should be better, because we know that there's noise in the data and regularization is good. So then the question we need to address is this fattest hyperplane, if we can find it efficiently, is it better than a thin one? Or is it better than outputting just a random separating hyperplane? Go for the fattest one. Okay, so let's start addressing these issues. Let's move to the board. Okay, so the question that we're going to address is, can we find the thickest hyperplane, the fattest hyperplane that separates the data? Okay. Can we find the thickest hyperplane / fattest hyperplane that separates the data? Okay, so that is the question that we want to address efficiently, of course. But, in order to discuss this question, we're going to have to talk about the geometry of hyperplanes. Okay, and here's the toy data set reproduced. Okay, so we have data points 0, 0, 2, 2, which are both minus 1, and 2, 0, 3, 0, which are both plus 1. So this is putting the data into the data matrix and the target vector, similar to what we did when we talked about regression. It's going to be convenient for the support vector machine for finding this optimal hyperplane. Okay. We call this the optimal hyperplane. Okay. Optimal in what sense? In the sense that it's the fattest hyperplane that separates the data. Optimal in the sense that it's most robust to measurement error. You can have large measurement error and it's still going to get E in 0. Okay. Now, let's look at this picture and we see that, okay, so if you have a typical hyperplane that separates the data, you put this cushion around the hyperplane and grow it, and you have to stop growing this cushion once you hit a data point. So the thickness of this hyperplane is essentially the distance or twice the distance to the closest data point. Okay. Doesn't matter what the sign of that data point is, it's the distance to the closest data point. So the thickness of the separating hyperplane is the distance to the closest data point. I'll box this. Not that it's a theorem or anything, but just it's important to understand, what is the thickness of the separating hyperplane, or of any separating hyperplane, in general, at least intuitively, visually, okay? And I'll underline two important words. The thickness of the separating hyperplane is the distance to the closest data point. So, for the moment, we're just going to focus on separable data. We'll deal with non-separable data later, just to build the concepts. Okay, and so it's going to be necessary for us to examine closely what does it mean for a hyperplane to separate the data. And you might say, oh yes, we all know what that means. Okay, fine. We'll quickly re-examine it. Okay, and then the second thing we'll have to talk about is, well, how do you compute the distance, to the closest data point? And before we discuss that, we'll have to discuss how do you compute the distance to any data point. Okay, so you have this generic hyperplane, and how do you compute the distance to a data point? Okay, so in order to sort of visualize matters, let me draw a picture of a hyperplane in 3 dimensions to show you how bad I am at drawing in 3 dimensions. So here's a hyperplane, so it's actually a plane. Okay. And, on one side of this hyperplane, you have, let's say, positive. On the other side of the hyperplane, you have negative. And on the hyperplane, essentially, we don't know what to do. So we'll see what's happening on the hyperplane very shortly. Okay. And so what is a hyperplane? So a hyperplane is a set of weights. Okay. Now, it's going to be extremely convenient to undo something that we sort of did earlier, which was, remember we had this input feature x. Okay, and we augmented it with a 1. Well, we're going to undo that process. Okay, so remember that before, or up until now, okay, your input x was this augmented feature vector with x0 equals to 1, x1, x2, up to xd. Okay, so this was in 1 cross r to the d. Okay, and the weights of a hyperplane were W0, W1 up to WD, which were in R to the D plus 1. Okay. And this first weight, which multiplies the 1, we call this the bias. Okay. So this is before. Okay. Now what we're going to do is we're going to undo this. Okay. And we're going to pull out the augmented 1. So now, or for SVM, okay, we're going to undo that. So the feature vector is just going to be the plain old feature vector, not augmented, x1, x2, up to xd. So this means that the weights are going to be w1, w2, up to wd. Okay? And we're going to have to separately deal with the w0, the term that multiplies x0, which was 1. So we're going to have a separate bias. Okay? And we could call it w0, but everyone calls it b, and it's a little bit less more convenient to call it b. So the bias is b. Okay, so before we had weights, now we have weights and a bias. Okay? But there's one less weight, and there's this special weight, the bias. Okay? So in this scenario, our hyperplane, our separator h of x was equal to the sine, okay, of w transpose x. In this scenario, there's no difference in the scenario, it's just a difference in notation. H of x is equal to the sine of W transpose X plus B. Where now, even though I'm using the same notation, W and X, before this was augmented, this was D plus 1 weights. Now this is not augmented, so this is D weights, and we pulled out the bias. So we call this, separating the bias. Okay, so i.e. now for support vector machines, we separate out the bias. Okay, and you might ask why. Why are we doing this? It was so convenient when we had PLA and pocket and linear regression to have the augmented X. Well, it turns out that, for support vector machines, for finding this optimal fattest hyperplane, and in general, the geometry of hyperplanes in the context that we're going to be discussing, the bias and the weights are treated differently. Okay? And so it's very convenient to not lump them together in the same vector because they're going to end up getting treated differently. Okay? All right. So now we can come back and say on one side of the hyperplane, the positive side, it's going to be the case, if you have a generic data point X, okay, it's going to be the case that, for a generic data point X, it's going to be the case that W transpose X plus B is positive. Here on the hyperplane, W transpose X plus B is equal to 0. And on the other side of the hyperplane, W transpose X plus B is less than 0. Okay, nothing new, okay, so far. Okay, now, something that's going to be slightly new, okay, is that we're going to redefine what it means to separate the data. Separating the data. Okay. So remember what it meant to separate the data. Sine of W transpose Xn plus B has to equal Yn. Okay, that's what it means to separate the data. So, your hyperplane, okay, and so let me define the hyperplane. Okay, so your hyperplane H is given by the weights W and the bias B. So your hyperplane separates the data if, when you compute W transpose Xn plus B and take the sign, you recover the Y value. Well, no surprise there. But now there's a very nice, convenient way of rewriting this condition, okay, which doesn't need this, messy, complex sign function. Okay, so this is equivalent to the statement Yn W transpose Xn plus B is greater than 0. So let's just quickly check. If Yn is plus 1, okay, for the sign to equal Yn, this must be positive. If Yn is plus 1, we're saying this must be positive. Okay, equivalent. If Yn is minus 1, the sign of this guy must be negative. And so that means that this guy must be negative. Okay, Yn is minus 1, we're saying that minus of this guy must be positive. So this guy must be negative. Equivalent. Okay, but now that raises the interesting, opportunity for us, which is that, okay, since they're all positive, since all these values are positive for n equals, 1 up to big N, okay, it means that there's some minimum value that's attained. So Yn W transpose Xn plus B, okay, the minimum value attained, min over N, is equal to rho. Some rho, we don't know what it is. Okay. And this encompasses the fact that this quantity is always positive. So it attains a minimum value, which is positive. So let me divide both sides by rho. It means that the minimum over n of Yn, W transpose over rho, Xn plus B over rho is equal to 1. We divided both sides by rho. And so that's interesting because, these are a set of weights that separates the data. Okay? And this new set of weights that separates the data, okay, is exactly the same hyperplane, okay, with just rescaled weights. Okay, so this is exactly the same hyperplane with rescaled weights. So that means that if you have any hyperplane that separates the data, there's an equivalent hyperplane. So there's an equivalent hyperplane geometrically, from the geometric perspective. So this is exactly the same hyperplane because if you rescale weights, you do not change the sign. So the final hypothesis, the hypothesis h of x, when you rescale weights by any positive number, is unchanged. So if you give me any hyperplane that separates the data, there's an equivalent hyperplane that separates the data according to this definition. It turns out, and so therefore this definition of separating the data and this definition of separating the data are essentially the same in the sense that this doesn't exclude any separating hyperplanes. It turns out that this definition is much more convenient for us. Okay. So we're going to now define what it means for a hyperplane to separate the data. I just want to emphasize that we're not changing what it means for a hyperplane to separate the data. We're just redefining algebraically the condition that we want satisfied for a hyperplane to separate the data. Sometimes these are called the canonical separating hyperplanes, but we don't need additional terminology. Okay, so, we're all comfortable with separating out the bias, so I'll erase this part. Okay. And let's define what it means to separate the data. So, definition. Okay. The hyperplane H, which is specified by weights and a bias, separates the data if and only if, okay, the min over all the data points, okay, of yn w transpose xn plus b is equal to 1. So this is the condition that we're going to use to say that a hyperplane separates the data. Now it's important to realize that any separating hyperplane, according to our old definition, can be represented according to our new definition by just rescaling the weights. So in some sense, we are choosing a scale for the weights. Intuitively, what's going on? Previously, when we separated the data, we could separate with an arbitrarily small value. So this signal could be arbitrarily small. Okay. Now we're saying that the minimum signal is +1. So if you compare the signal to 1, the further it is from 1, the more you are from the hyperplane. So 1 sets a sort of an absolute length scale against which we can sort of, in some sense, compare and compute distances. Okay. All right, so we have just made a little more precise what it means to separate the data, more precise in a way that's going to be helpful. Okay. Right. Now let's address the issue of the fattest hyperplane. And we already agreed that the fatness of a hyperplane is equal to its distance to the closest data point. So before we can even compute the fatness of a hyperplane, we need to be able to compute the distance of a data point to the hyperplane. Okay. So computing the distance of a point x to the hyperplane H, which is given by its weights and bias WB. Okay, so let's talk about that. Okay, so we've not started even talking about computing or finding the fattest hyperplane. We're just, developing some preliminary familiarity with the geometry of hyperplanes. Okay, all right. So let's call this the distance from X to H, where H is specified by W and B. Okay, well, what is it? Let's look at this picture and see. Well, what you do is you drop this perpendicular to the hyperplane, and you want the distance of that perpendicular. Now, let us take any point x on the hyperplane. So let's call this point x. So let us take any point x1 on the hyperplane. Okay. One way to compute this distance is to take the vector from x to x1. So let's take the vector from x to x1. Okay. And if we had a unit normal, so u is a unit normal to the hyperplane, okay, then the distance from x to the hyperplane, so the distance of this perpendicular is basically the distance of this perpendicular times the distance from x to x1 times the cosine of this angle. Okay, so the distance from x to x1 times the cosine of this angle is exactly this distance. But the dot product between this vector and the unit normal is exactly this distance times the distance, the length of the unit normal, times the cosine of that angle. Okay. So this is exactly equal to the absolute value of the unit normal dotted into x minus x1. X minus x1 is this vector, or x1 minus x, it doesn't matter because I'm going to take the absolute value. You dot it into the unit normal. So this is the norm of this, which is 1, times the norm of that, which is whatever it is, times the cosine of this angle. This length times the cosine of that angle is exactly that perpendicular distance. Okay. So if I could compute a unit normal to the hyperplane, then I can compute the distance. Okay, so let me show you something interesting. Okay. The weights that define the hyperplane are exactly in the direction of this normal. So I claim that u equals w, okay, but that may not be a unit, divided by the norm of w, is a unit normal to the hyperplane. Okay. So fundamental fact of hyperplanes. The weights W that define the hyperplane are indeed the normal to the hyperplane. In fact, the hyperplane is defined as the set of points that are normal to the weights. Okay. Now that defines actually infinitely many hyperplanes, and that's where the bias comes in to set which of those infinite hyperplanes to pick. Okay. Now for those of you who know this fact, well, this is going to be a little bit of review, so sit back and relax. But if you don't know this fundamental fact, pay attention, because this is a truly fundamental fact about the geometry of hyperplanes. Okay. So let's prove it. Let's take any point on the hyperplane that's not x1. Okay. And so there's the vector. So this is a way to define a vector in the hyperplane. So let's call this x2. So x2 minus x1 is a vector in the hyperplane. Okay. So this is a vector in the hyperplane. Okay, I'm going to prove that W dotted into this is 0. So W dotted into x2 minus x1 is 0, no matter what that vector is that you chose in the hyperplane. That would mean then that W is perpendicular to the hyperplane at any x1. Okay? Because you can from x1 take any vector going out of x1 that's in the hyperplane, and I'm going to show that W is perpendicular to that. Okay, so here's the proof. This is W transpose x2 minus W transpose x1. But what do we know about the hyperplane? If these 2 points are on the hyperplane, W transpose x1 plus B equals 0. W transpose x2 plus B equals 0 because they're on the hyperplane. Okay. So subtract. This says that W, so this minus that, the B's cancel. W transpose x2 minus W transpose x1 equals 0. So this equals 0. So W dotted into any vector that's on the hyperplane is 0. So W is normal to the hyperplane. So that means that U, which is W over norm of W, is a unit normal. So the distance, okay, from a point X to a point H is equal to, okay, the absolute value of U, which is W, okay, over norm of W, dotted into X minus X1. Okay. And this is equal to, okay, we can pull out the absolute value of W from this because it's dividing the whole thing and it doesn't affect this absolute value. So this is 1 over the absolute value of W, okay, times W transpose X minus W transpose X1 in magnitude. Okay. But this is equal to 1 over the norm of W. W transpose X plus B minus W transpose X1 minus B. All I did was I added and subtracted B. Okay, but W transpose X, so this is minus of W transpose X1 plus B. So this term here, well, X1 is on the hyperplane. So this term here is just 0. So this term here is 0. So this is equal to the magnitude of W transpose X plus B divided by the norm of the weights. Okay. So this is the signal that X generates for my hyperplane. Okay, so remember I told you now the signal will be playing a concrete role in determining distance. So this is the signal that my weights, my X generates, but you normalize the signal by the norm of the weights. Okay, so now I want to sort of just spend a short moment, explaining to you why we separated out the bias. Okay, so here are 2 reasons why, separating out the bias was very convenient. First, the unit normal is the weights divided by the norm of the weights, and there's no bias involved here in determining this normal. So it helped that, we didn't have to deal with the bias, the W0 component here. So that gives the unit normal a particularly simple form. Okay. And now when you look at this distance from a point to the hyperplane, the bias and the weights play different roles. Okay. On top, the bias and the weights play the same role if you imagine the bias being multiplied by the augmented. But in the bottom is just the norm of the regular weights, and this does not contain the bias. Okay. So if you look here, and you look here, you see that W and B are being treated differently. And that's because when it comes to the geometry of hyperplanes, the bias and the weights play different roles. The weights determine the normal direction to the hyperplane. The bias determines the shift. And that's what's coming out here. That's why we had to pull out the bias. Okay? So, with that, let me summarize that short discussion of the geometry of hyperplanes in one formula, okay, which is the distance of a point x to the hyperplane h, which is given by the weights and the bias. So the distance from x to h is equal to the signal, the magnitude of the signal, W transpose x plus b, divided by the norm of the weights. Fantastic. Okay, so now let's erase. Okay, so let's talk about the thickness of a given hyperplane. Remember, we're not even close to getting the fattest hyperplane. We just want to say, if you give me some random separating hyperplane, can I find its thickness? Can I determine the thickness of the hyperplane? So determining the fatness or / thickness of a separating hyperplane. Okay. Well, let's go back to this picture and remember that the thickness of the hyperplane corresponds to putting this cushion and expanding it until you hit the closest data point. So the thickness of the hyperplane is exactly the distance to the closest data point. So the thickness, and we typically call this the margin. Gamma of h. Remember what is h? H is a hyperplane, WB. So the margin, gamma of h, is equal to the distance from h to the closest data point. And that should jive with your intuition from that picture. You expand the cushion and you stop when you get to the closest data point, and that's the thickness. Well, it's twice that, but factor of 2, who cares about the factor of 2? Okay. Well, let's say we're finding the half distance or the half thickness. Okay, so what is the distance to the closest data point? It's the minimum over all my data points of the distance from xn to h. That's all that. I'm just rewriting the top line, which was English, now math speak. Okay, and we now have an expression for the distance. Bam. Okay, so this is the minimum over all my data points of the absolute value of W transpose xn plus b divided by the norm of W. Well, this norm of W doesn't depend on xn, so I can pull it outside the minimum. So this is equal to 1 over the norm of W, the minimum over your data points of W transpose xn plus b. Okay, now, can anybody tell me what this is? I'll give you a couple of seconds. Pause the video. I'll give you a few seconds. 1, 2, 3, 4, 5. Can anybody tell me what that number is? Well, you see something similar here? Okay. So, let's look at this guy. Okay. So the minimum over my data points of yn W transpose xn plus b equals 1. But that means that each of these numbers is positive. Okay. So the minimum over n of yn W transpose xn plus b. Okay, this is equal to 1. But that's equal to the minimum over n of the magnitude of yn W transpose xn plus b. Okay, why? Because these guys are all positive. So a positive number equals its magnitude. And the magnitude of a product is the product of the magnitude. This is the minimum over n of yn W transpose xn plus b. And what's the magnitude of yn? That's one of the convenient things of making our yns plus or minus 1. So in some places you will see that people define classification as 0 or 1. Well, it's much more convenient to define it as plus or minus 1. Because the magnitude of this yn is now 1. So this is the minimum over my data points of W transpose Xn plus B. And this is equal to 1. So now you see why it's so convenient that we sort of made a much more precise definition of what it means to separate the data. Okay, because it simplifies this expression considerably. It says that the thickness of a hyperplane, so this quantity is 1, because we're only interested in the thickness of a separating hyperplane, and a separating hyperplane satisfies this constraint through its definition. So the thickness of a separating hyperplane is equal to just 1 over the norm of the weights of the hyperplane. Very nice. So let me summarize that also here. So here we're building up a nice catalog. It's always nice to have a catalog. You know, people like catalogs. You can order from them toys or whatever. But we're getting a set of very beautiful toys in our catalog. Okay, so the thickness of a hyperplane, so the thickness of a hyperplane. Okay, so gamma of H, and H depends on, you know, W and B. And this thickness is sometimes called the margin. So you will hear people say the margin of a hyperplane is equal to 1 over the norm of the hyperplane's weights. Okay. Now I should be more specific of a separating hyperplane. Okay. And let's just pause a few seconds to just think about what does this, you know, depend on. And it looks suspiciously like the thickness of a hyperplane depends only on the weights of the hyperplane. The thickness depends on the weights. It's just 1 over the norm of the weights. So I want you to pause for a second and think, what else does it depend on? And this is very important. Okay. Even though it looks like it only depends on 1 over the norm of the weights, it depends on something else. 1, 2, 3, 4, 5. Well, if you're coming back and you just want to be here for the ride, remember, the thickness of a hyperplane also is defined with respect to a data set. If I had no data set, the thickness is infinity. I can just expand the cushion as much as I want. The reason the cushion is finite is because of the data set. So this guy depends on the data set as well as the weights. Okay. So where's the data set? It looks like the data set has disappeared. Where's the data set? 1, 2, 3, 4, 5. If you're coming back and you figured it out, the data set is embedded in this notion of separating. Okay. And it's embedded in here. So these weights must satisfy a constraint, okay, that they separate the data. And so that's where the data comes in. So the data has a role to play in the weights. The data influences the weights. Okay. So now we have a precise sort of definition of what it means to separate the data, a convenient definition. It's not that what we had before was not precise. We know how to compute distances, and we have miraculously gotten a very simple expression for the fatness of a given hyperplane. Okay? And so, well, the task of finding the fattest hyperplane is to simply find the hyperplane with the largest margin that separates the data. So finding the fattest hyperplane means maximize 1 over the norm of the weights, subject to the constraint, subject to the fact that it separates the data. The minimum of your data points, what does it mean to separate the data? Yn W transpose Xn plus B equals 1. So, let me just massage this a little bit. Okay. Turns out that, so we're done. Well, let's massage this a little bit, okay, to put it in a much more convenient form. Now it's mathematical convenience, okay. We're conceptually done. Maximize 1 over the norm of the weights is equivalent to minimize the weights. Okay, so that's equivalent to, so this is equivalent to minimize the norm of the weights. Okay, so this is equivalent to minimize the norm of the weights. But if you're minimizing the norm of the weights, that's equivalent to minimizing the norm of the weights squared. Okay, and minimizing the norm of the weights squared is equivalent to minimizing half the norm of the weights squared. I can put a half here if I want. And so then It's equivalent to minimizing the norm of the weight squared, half the norm of the weight squared, which is equivalent to minimizing 1/2 W transpose W. So finding the fattest hyperplane is equivalent to the following now mathematical problem. Here we talked about, we can think about visually moving the hyperplane around until it has the largest thickness. That corresponds mathematically to the following optimization problem. Okay. So we have reduced the task to solving an optimization problem. This is an example of an optimization problem. Okay. And now let's massage this optimization problem a little bit to get it into its final form, and that's the form that is typically used. Okay, so let me erase this. Okay. So minimize 1/2 W transpose W subject to the min of over all your data points of yn W transpose xn plus b equals 1. Okay, well, certainly if if the minimum is equal to 1, it means that yn W transpose xn plus b is greater or equal to 1. So we could consider an alternative optimization problem with this constraint. So minimize 1/2 W transpose W subject to this inequality constraint, where I replaced equals to 1 with greater or equal to 1. Okay. Now, certainly, if you solve this problem, you have a solution to this problem. So the feasible set here is larger. But I claim that when you solve this problem, you will have solved this problem. So let's see why. So the only consideration is that what if all these values are strictly greater than 1? So there's no value that's equal to 1, making the minimum equal to 1. If there's no value that's equal to 1, they're all greater than 1. Okay, it means that I can shrink W and B and lower the values a little bit. If I can shrink W and B, I've lowered the norm of the weights. So then I'm not at an optimal for this problem. Okay. So I'm claiming, and now you can sit down and prove rigorously, that if you're at an optimal for this problem, it will necessarily be the case that one of these constraints will be saturated. And that means that the minimum will not only be greater or equal to 1, it will be equal to 1. Okay. So these two are equivalent optimization problems. Okay. These constraints are not equivalent constraints, but these are equivalent optimization problems. What that means is that any solution to this problem, if you solve this problem, it will be a solution to this problem. It will be an optimal for this problem. If you solve this problem, it will be an optimal for that problem. But the feasible sets are different. And if you think about it, think about when we talked about regularization. The regularization constraint was W transpose W less equal to my budget C. And then we made the argument that, it suffices to only have to consider the situation W transpose W equals C. Okay. So there are many situations where you can expand the feasible set and make the optimization problem easier, okay, in the comfort of knowing that the solution will satisfy your original stricter constraint. Okay, so these are equivalent optimization problems. So it means that we can equivalently find the maximum margin hyperplane by minimizing the norm of the weight squared, okay, with a half, minimize the norm of the weight squared subject to inequality constraints. Subject to yn W transpose xn plus b greater equal to 1. Now why is this more convenient? Because we don't have the messy min. Okay, so we just have an independent constraint for each data point. So here, let me make some observations. What we're minimizing, so what do we have to choose? We have to choose W and B. So my variables in the optimization are W and B. Let's look at what we're minimizing. That's called the objective. The objective is quadratic. Okay. And the constraints in terms of W and B are linear inequality constraints. Linear inequality constraints. Okay. So this is a quadratic optimization problem with linear inequality constraints. This is an example of what is called a quadratic program. This is a quadratic program. Or sometimes we abbreviate it to QP. Okay, so let me erase. Okay. And let me show you how we solve this problem. At least let's do an example with that case. Let's find the optimal hyperplane, the fattest separating hyperplane for our little toy example. Okay. So it means that we have to solve this optimization problem. So what do we have to find? We have to find W1, W2, and B. Okay. And we have to minimize 1/2 times the norm of the weights. So we have to minimize 1/2 W1 squared plus W2 squared. Okay. And we have several constraints to satisfy, one for each data point. So let's take the data points one by one. Okay, so for data point 1, this y is negative, so we have, and x is 0, so we have negative b greater equal to 1. Negative b greater equal to 1. Data point 2, this is negative, and now x1 and x2 are 2, so we have negative of 2x1 plus, 2w1 plus 2w2. So this is W transpose X, where both of the components of X are 2 and 2. Okay, plus B is greater equal to 1. Okay, and then the other two data points, Y is plus 1, so we have, and X2 is 0, so we only get W1 coming in, so we have 2W1 plus B greater equal to 1, and 3W1 plus B greater equal to 1. So these four constraints are exactly all these constraints. Okay, so these constraints must apply for n equals 1, 2, up to big N. Okay, so let's solve. Well, if you solve, let's see, if you add this and this, the b's cancel, so you get 2w1 greater equal to 2. This implies w1 greater equal to 1. If you add this and this, then we get that the two w1s cancel, the b's cancel, so we get minus 2w2 greater equal to 2. This implies that w2 less equal to minus 1. Okay. So since we're trying to minimize the norm, we want to choose the magnitude of the w's as small as possible. The smallest you can choose is w1 equals 1 and w2 equals minus 1. And it turns out that you can satisfy all these constraints with also choosing b equals to minus 1. Okay. So b equals to minus 1 is a solution. And so we've got our weights and our bias. So sine, so h of x, h optimal, so fattest, h fattest of x is equal to the sine of w1 x1, which is x1, minus plus w2 x2, which is minus x2, plus b, which is minus 1. Okay. So that's not optimal. It turns out that optimal has to rotate a little bit. So let me draw for you what optimal looks like. Optimal is something like this. And the thickness of the hyperplane is 1 over the norm of the weights. The weights are 1 and 1, so the thickness 1 over the norm of the weights, which is the margin, is equal to 1 over root 2. So the thickness here is 1 over root 2, or 0.707, something like that. Okay, and the hyperplane is such that when you expand your cushion, it hits those two red points and it hits this blue point. Now, it should be obvious to you that it should hit a red point and a blue point simultaneously when you have the optimal hyperplane. Because let's say that there's room left on the blue side, then you can shift the hyperplane a little bit and expand. Okay? So the fattest hyperplane will always hit the red and the blue points simultaneously when you reach the maximum fatness. Okay? That's not true for a non-optimal hyperplane. Now, I'm going to box some data points here. It hits these guys simultaneously. So those, you can think of these data points that it hits simultaneously as we're expanding the cushion as supporting data points. They're what prevents it from expanding more. So these data points are called supporting data points or support vectors. Support vectors. Okay. They are what prevent it from expanding more. I want to make another very important observation. It'll be useful later. What about this guy here? So what about this data point? It's not a support vector. An interesting observation is if I threw that data point away, would my optimal hyperplane change? Okay, so let's see. I throw this data point away. Well, whatever the hyperplane that remains, and certainly separates the data that remains. Okay, because it was a separating data point when I didn't throw it away, and now that I threw it away, it cannot fail to separate the data. The only question is, now that I've thrown some data away, can I make it larger? No, because it's not one of the supporting points. So the optimal hyperplane will not change when I throw away this data point. And intuitively you can look at this and say, well, that looks like a redundant data point. And indeed it sort of is. So in order to define this optimal hyperplane, I only need to know what are my supporting vectors. Very interesting observation. To define / find the optimal / fattest or max margin hyperplane, it suffices to only have the support vectors. The other data are, in some sense, redundant. So all the information necessary for constructing the optimal, the most robust to noise hyperplane is embedded in the support vectors. So in an indirect way, okay, the optimal hyperplane identifies the important data point. So what a beautiful byproduct of this algorithm. Okay, right. Okay, now, we are not going to solve by hand this problem every time we have a data set to sort of separate and find the fattest, most robust hyperplane. Okay, so we need an algorithm. We're not going to solve it by hand. And the good news is that the folks over on the mathematical side, in the optimization arena, have solved this problem beautifully for us. Okay, using what is called quadratic programming. So we're not going to solve the quadratic programming problem. They have solved it. They have developed algorithms. We're going to use their algorithms for quadratic programming. So next, I'm going to tell you how we solve this problem on a much larger scale, where we can't solve it by inspection and manual algebra. Okay. So we'll come back. Let's talk about quadratic programming. Okay, so let me tell you about quadratic programming. So first, let me tell you what is a quadratic program. So quadratic program. Okay, so this is an optimization problem. Okay, and that it's formulated. You can have it in many different ways, and I'm going to formulate what I'm going to call a standard version or a quadratic program in standard form. And different people have different conventions, so be careful. Okay, so. A quadratic program in standard form is an optimization problem. You have to minimize something. So you minimize, 1/2 U transpose Q U plus P transpose U, subject to A U greater equal to C. Okay. So you say, what? Okay, well, you can't argue with me. Okay. That's what a quadratic program is. Okay. You minimize a quadratic term plus a linear term. So Q has to be positive semi-definite, ideally positive definite. So Q is a matrix. That's Q. That I'm gonna call its dimensions Q by Q. Okay. P is a vector. Okay. So it's gonna have dimensions Q by 1. Okay. A is a matrix, and it has dimensions, let's call it n by q, and C is a vector. It has dimensions n by 1. Okay. So now, in what sense is this an optimization problem? So you are supposed to find U. So minimize over U. Okay. And what's the dimensionality of U? The dimensionality of U is it's a q-dimensional variable, so in R to the q. And so that's where all this q comes in. So I'm specifying a quadratic program in standard form. Okay. Now, different mathematical packages may define it in a different way. Sometimes the most common way in which packages might differ is instead of AU greater equal to C, they might have AU less equal to C. Well, that just corresponds to flipping the sign of A and C. Okay, that's not hard to do. Okay. So Q, P, A, and C are user-defined parameters. Okay. So you get to define these. You get to set these. Okay. And implicitly, when you set these, it implicitly defines Q. So you give me a Q by Q matrix, you give me a Q by 1 vector, you give me an N by Q matrix, and you give me an N by 1 vector. Okay? So these are parameters. Okay? So you can imagine that you feed these parameters, so Q, P, A, and C, you feed them into a quadratic programming algorithm, QP. Let me call it QP. Okay. And what does this quadratic programming algorithm do? It returns a vector U. Let's call it U star. Okay. And what's the property that U star satisfies? It satisfies the property that it solves this optimization problem. In other words, among all U's that satisfy my constraints, the one that's returned minimizes the objective. So that's the definition of a quadratic program. Okay, you can't argue with me. That's the definition. Now, turns out that the mathematicians, the optimization folks, have figured out efficient sort of interior point, methods that can solve these quadratic programs efficiently. Okay, and any reasonably good mathematics package, MATLAB, Python, blah, 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 they all have quadratic programming tools. Now, they may call these parameters Q, P, A, and C, they may call them by different names, but essentially all these parameters are there. Okay? And you specify these guys, and out pops U star, the optimal. Okay? So, what I'm going to show you is that we can use such a package, okay, to solve the problem of finding the optimal hyperplane, the fattest separating hyperplane. So in other words, what I'm going to convince you is that this is a quadratic program. And once I convince you that this is a quadratic program, it will mean that I will have identified what are Q, P, A, and C, and then I can just plug them in, okay, and out will pop the optimal U star, the weights that satisfy this, that solve this optimization problem. So let's see what's our optimization problem. Remember, U are the variables. So what do we have to decide? We have to determine B and W. So we have to determine B and W. So let's define U equals B and W. So let's combine B and W into one vector, because that's the way in which this program is formulated. So we're combining B and W into one vector. Okay. And what we want to minimize is 1/2 W transpose W. So we want to minimize 1/2 W transpose W. Here we see that we're minimizing, some complicated thing. 1/2 U transpose QU plus P transpose U. So we have to minimize 1/2 W transpose W. Well, the 1/2s are both there, so that's convenient. Okay. So let me focus on the W transpose W bit. W transpose W is equal to, okay, so now you can fill in the details, is equal to B W transpose 0 the identity, D by D identity, okay, the D by 1 vector transpose of zeros, the D by 1 vector of zeros transpose, and the D by 1 vector of zeros, okay, times B W. Okay, so let's see. So when you do this matrix product, you get this times this times this. So that's 0. You get this times that, which is 0. Okay. You get this times that, which is 0. Okay. And you get this times this, which is W transpose the identity, W, which is W transpose W. But now this is just exactly U transpose times this matrix, 0, 0, D transpose, so that's D, you could write that as the D by 1 vector, vector transpose, 0, D, and then I, D by D. U, and so this guy here is our Q. So for us, Q is exactly equal to a matrix, which is 0, a row of zeros, a column of zeros, and the identity, D by D identity. Okay. All right, what about P? Well, so this is called the quadratic term, this is called the linear term. If the quadratic term is 0, actually, this is called a linear program, but we are dealing with quadratic programming. So in our case, we have the quadratic term, we have no linear term. So P is just equal to the 0 vector. Now, how many dimensions in P? 1, 2, 3, 4, 5. Well, if you solved it and you said D plus 1, you're correct. So this is a D plus 1 dimensional vector of zeros. Okay. So we have identified that this term, 1/2 W transpose W, corresponds to the objective in a quadratic program if I set Q this way and P that way. Okay, so that's the first step in sort of mapping any optimization problem to a quadratic program. Identify the optimization variable. So we identified that. Figure out what Q is. We figured that out. And figure out what P is. We figured that out. Okay. Now let's look at the constraints. These constraints look nothing like those constraints. So let's look at the constraints. So one of our constraints is, for example, y1. We have the constraint y1 W transpose xn plus b. W transpose xn plus b. Okay. So that's equal to y1b plus y1 times xn transpose w. Sorry, x1. This is x1. x1 transpose w. Okay. But now I will observe that this is exactly y1. Okay, y1 x1 transpose matrix multiplied by the vector b w. Because here I get y1b plus y1 x1 transpose w. Okay? All right. And this is just u. So this is equal to, so I'll rewrite it now. This is y1 transpose, y1 x1 transpose times u. Times u. Okay, let's look at the second constraint. y2 w transpose x2 plus b. That is going to equal y2 x2 transpose u. Okay, and we can keep going. yn w transpose xn plus b. That is going to equal yn xn transpose times u. Now I can collect all these rows in a matrix. So this is all these together, can be captured compactly in one matrix, which is y1 x1 transpose, y2 x2 transpose, y3 x3 transpose, yn xn transpose. So those rows, each of these rows, I've collected them up in a matrix, and now I have my u. Okay. And in each case, I need this. I need each of these to be greater equal to 1, greater equal to 1, greater equul to 1. So those were my constraints. Okay. So here are all my constraints. So here's the first row, the second row, the third row, and so on, the nth row. So this has to be greater than or equal to, in the vector sense, the vector of 1s. Okay, so if I call this matrix A, let's look at this matrix more carefully. Well, remember before we had the data matrix X, which was 1 x1 transpose. Well, now this row is just multiplied by y1. This is y1, so this here is y1 times the row 1 x1 transpose. So that was a row in my data matrix. y2 times the vector 1 x2 transpose. So you can think of this as I take my rows in my data matrix and just multiply them by the y values. Okay? So we can think of this as the signed data matrix. Okay? We call it A. So AU greater equal to the vector of 1s. AU greater equal to C. We have identified A for our problem is the signed data matrix. Okay, so I'll write it as y1 x1 transpose, so that's a row. y2 x2 transpose, so that's a row, and so on. yn xn transpose, so that's a row. So A, and this is an n by q matrix, n by d plus 1. Q is d plus 1. And then what is C? Look here, C is just a vector of 1s. So C is just a 1 vector, which I'll write as 1 d plus 1. So the d plus 1 vector that's composed entirely of 1s. Okay, so let me erase this. We've just derived that. Now let me tell you what we have derived. Okay, so summary. What I have done is I have shown you that this optimization problem, by suitably massaging it, okay, can be put into the standard form of a quadratic program. What that means is that I have to identify Q, I have to identify A, P, and C. So when you get your data, if you set Q this way, if you set A that way, if you set P this way, and if you set C that way, then you feed it into a quadratic program, it spits out U star. Okay. That U star okay, so it spits out U star. That U star will be equal to B star W star, your optimal weights and bias. So you construct Q, P, A, and C. Feed it into the quadratic program, boom, it spits out U star. You take the first component of what it spits out, that's your optimal bias. The remaining D components, those are your optimal weights. Okay, so exercise. For our toy data set, exercise. For our toy data set, I'll remind you, X was equal to 0, 0, 2, 2, 2, 2, 0, and 3, 0. Okay. And Y was equal to minus 1, minus 1, plus 1, plus 1. So this was our toy data set. Show. Okay, now sit down and do this exercise by hand, Okay, show that Q is equal to, well, Q is equal to 0, 0, 0, 0, 1, 0, 0, 0, 1. They show that A is equal to 0, 0, minus 2, minus 2, 2, 0, 3, 0. Show that P is equal to 0, 0, 0. And show that C is equal to 1, 1, 1, 1. Okay? Okay, so show that. Just show it. And then feed in this QP. So figure out what package you're going to use and feed in this Q, P, A, and C. Okay, so feed in these guys. Q, P, A, and C into your favorite quadratic program solver. Okay. And out should spit. Let's see if you can figure it out. What should it spit out? I'll give you a few seconds. 1, 2, 3, 4, 5. Okay, if you're coming back for the ride, okay, here it goes. Oh, and if you said this, man, you are fast. Okay, so it should spit out minus 1, 1, minus 1. Well, if I put it in that kind of vector form, it should spit out minus 1, 1, minus 1. So if you said that, you got it. And how do I know that? Because we solved this problem by hand. And we got W1 equals 1, W2 equals minus 1, and the bias was minus 1. Okay. Now it turns out, okay, that this problem, as long as you have at least one positive data point and one negative data point, this is a convex optimization problem. It has a unique solution. And so, we solved it one way. So now the quadratic program must reproduce that solution. Okay, so exercise, go and do it. Okay. Meanwhile, okay, let me summarize the algorithm for finding the fattest hyperplane, and let's end with a little bit of discussion. Okay, so welcome to the slides again, and I'm going to just summarize the algorithm for you. So you have a data set. Okay, so the first thing you do is you construct a signed data matrix, which is the data matrix that we had before, but now each row you multiply by the corresponding y value, plus or minus 1. So that's the signed data matrix, and you construct your quadratic form matrix Q, okay, which is zeros in the first column, zeros in the first row, and then the identity in the bottom right. The identity matrix D by D. Okay. You construct your linear term, your linear part of the objective, which is just the zero vector, and you construct your vector of ones, which is C. So now you take your favorite quadratic programming algorithm, your favorite quadratic programming package, okay, and you feed in Q, P, A, and C into this quadratic programming package. Out it spits U star, okay, and then U star has two essential components. The first component is the optimal bias B star, and then the remaining D components are the weights W star. So that's a very simple algorithm. And so the efficiency of this algorithm entirely depends on what algorithm you use to solve the quadratic program, and that's an area of research. There are, iterative algorithms, there are, interior point algorithms, there's the simplex algorithm, and so there are many approaches to solve it, but that's not our business. We outsource that to the very good mathematicians, the optimization guys. Okay. And then your final hypothesis, is g of x is, the sign of w star transpose x plus b star. And what is the property that this final hypothesis satisfies? Well, it's a linear separator, so it's a perceptron. So it has all the generalization properties of the perceptron, VC dimension and all of that. Okay. But now, it intuitively is the most robust. It's the maximally regularized. It's most tolerant of measurement error. It's the fattest hyperplane that separates the data. Okay, you might wonder, what do we do when we can't separate the data and so on? We'll deal with these details later. But now we see this beautiful concept that we can get the fattest separating hyperplane, the most robust separating hyperplane. It's just quadratic programming. Okay, and the nice thing about quadratic programming is we have, polynomial time algorithm to solve this problem essentially exactly, because it's a convex optimization problem, because in our case, the matrix Q is positive semi-definite. So as long as you have at least one positive and one negative data point, boom, okay, you get the optimal separating hyperplane, the fattest separating hyperplane. So let's look at an example. So here's an example. I just generated some data. The target function is the horizontal flat line. You can see the boundary between plus and blue and red. I generated a bunch of data. I ran that algorithm. Now I can't solve it by hand anymore. Okay, when I ran the algorithm, it produced this thick black line, and the corresponding thickness is illustrated by the gray lines. And you can see that as you increase the sort of cushion around this thick black line, it simultaneously hits these two blue points and that red point. What's interesting is if I throw away all the other blue points and all the other red points, I would get exactly the same separator. Wow! Okay, wow. Okay, so I've identified not only the optimal separator, but also simultaneously the important data points. Now, this algorithm is in some sense deterministic. Once you give me the data, boom, the optimal fattest separating hyperplane is unique, it's well defined, you can find it with quadratic programming and all the good stuff. Okay? Now let's see what would happen if we ran PLA. Now, because I know the target function, I can compute E out. So you can see that E out for this optimal separator is not quite 0. To be 0, you need the flat red guy. Now we can run PLA, and PLA picks a random data point, and at every iteration, picks a data point that's misclassified and updates and goes, and eventually separates the data. So you could get, now follow my mouse cursor, you could get the separator that looks something like this, or you could get the separator that looks something like that, okay, or you could get the separator that's close to the target function. Okay. And that depends on the order in which you present the data, which random misclassified point you take at each PLA iteration. So there's a lot of randomness in the PLA. And that means that the final hypothesis you produce is in some sense a random final hypothesis. It separates, but it could be anything. And so on the right, I'm showing you the E out for the support vector machine. And that's deterministic in some sense. It doesn't matter about order, nothing. Okay. It's just a quadratic program. Okay. And then, if you run the PLA, you get a whole bunch of separators. And if you're lucky, you can get a separator that has better out-of-sample error, okay? Depending on the order in which the data points pop up. But if you're unlucky, you can get a separator that's much worse. Okay? And they're all separators. They all have the same E in. Okay? So, support vector machine, is this nice, stable, robust classifier. Okay? And, the PLA would give us this array of classifiers, final hypotheses with a wide variety of out-of-sample error. That's just a comparison of the support vector machine with the perceptron learning algorithm. Okay. Both of them produce a separator. The support vector machine is in some sense the most robust. Now, let's link the robustness of the support vector machine, which we have so far intuitively argued, let's link it to regularization. So I'm going to just end on just a slide that shows the analogy. Okay. The support vector machine says, I'm going to minimize the norm of the weights. Okay, that was the program, the quadratic program, the optimization problem that we just had. I'm going to minimize the norm of the weights subject to the constraint that you fit the data. So find me the most robust separator. Okay. When we studied regularization, remember we talked about let's give ourselves a weight budget, okay, and we'll minimize the in-sample error subject to that weight budget. So now let's put this in this table and compare. Regularization says minimize the in-sample error, okay, subject to a budget. So in some sense, you can think of the optimal hyperplane as, optimally regularizing. So using the smallest possible budget while trying to get the in-sample error 0. Think back to Occam. Use the simplest hypothesis that explains the data. So this is in some sense, the optimal hyperplane is in some sense a literal implementation of Occam's razor. And you see the similarity. In both cases, we're trying to sort of constrain the complexity of the final hypothesis. in the support vector machine, in the optimal hyperplane algorithm, we're explicitly minimizing the complexity. In the regularization approach, we are minimizing the in-sample error while I give you a budget of complexity. So you see the similarity and the link between the fattest hyperplane and regularization. But we arrived at the fattest hyperplane intuitively as it's most robust to measurement errors in the data. Okay. So now we have multiple reasons why we think that the fattest hyperplane is good. It links to regularization, it's most robust to measurement errors in the data. Okay. So can we, in some sense, investigate that in a more quantitative, more principled manner? So this lecture was spent on the algorithmic issue. Okay. So we intuitively sort of justified the fattest hyperplane as the one that's most robust to data and asked, can we efficiently find it? The answer is yes. Okay. And we can even get more efficient than quadratic programming, because quadratic programming in very high dimensional data and very large amounts of data is essentially an n-cubed algorithm, where n is the number of data points, and the proportionality constant in that order of n cubed is related to the dimension. Okay. So it's dn cubed. So even though it's a finite algorithm, just like the pseudo inverse algorithm for regression, we now have an exact algorithm for classification. Even though it's a finite algorithm based on convex optimization, it's still not necessarily very efficient. Okay. So a lot of research is done on making it more efficient, and we'll talk a little bit about that later. Okay. Especially when you go to high dimensions, it can get extremely costly. But now we've at least established the feasibility of being able to find the fattest hyperplane efficiently. Okay, so let's now, next lecture, talk about, is it the case that the fattest hyperplane or fat hyperplanes in general are better than thin hyperplanes? Next time. For now, checking out.